to inviting me in New Zealand. It's an honor, and I'm very glad to be here. Also, I would like to thank my colleague and friend Thomas from Sylvan, Australia, to welcome me a few days ago in Australia. I don't know if you know, but Thomas, before he joined Sylvan Australia as general manager, was working with the research team very closely, and is one who discovered very early the potential of Tuscany 20 at developmental stage. And after, when he joined the crop year, he helped us to launch and to create solid data for the patent of Tuscany 20. So without Thomas, Tuscany 20 won't be Tuscany 20. Thank you, Thomas. So here today to talk about the global Sylvan breeding research program, because it's a global program, because we have a global research team. We have several research centers at Sylvan. We have a research center in America, in Kittanning, Pennsylvania. We have one in France, in Langeais, where I'm in charge. And we have a team in China, and we hope that we're going to expand this research team there in Wuhan, where we have our Sylvan plant. So I will start with the definition of breeding. So what it is. It's the science of creating new varieties, fulfilling more and more human needs. It's a gradual building of genetic material. At Sylvan, we dedicate a lot of resources to this research program. For what? First of all, for more. We try to create variety that increase yield, because the history of agriculture shows that the half of the development in crop yield arrives from breeding. We want better. We want variety that adapt to cultural limitation, to climate, cropping, harvesting, canning condition. Variety that resist to pests and disease with higher quality. By higher quality, we mean with better shelf life, with darker cap for brown, but we also try to fight the risk of genetic erosion. We want to breed different. We want to introduce novelty for our market, for diversification and segmentation. We have different ways to improve the breeding. So by improving the genetic gain, so we can play on variation, intensity, accuracy, and reducing time. By variation, we talk about the breeding stock. Bigger the germplasm is, better it is, because you have more genetic diversity. The intensity will be reflected by the number of crosses. So at Sylvan Europe, for example, we try to breed at least to make at least 1,000 crosses. We're going to be more accurate by the good phenotyping. With a deep and precise phenotyping, we will increase the accuracy. And we will try to reduce the time by using a molecular marker or new technology. So at Sylvan, we have different breeding research programs. Of course, we have the historical white button mushroom research program that mainly done in America. In Europe, we are in charge of the brown button mushroom, even if America participate a little bit, but main of the work is done in France. And in France, we developed, since 3 to 4 years ago, new exotic breeding program in shiitake and Proteus austratus. So quickly, this is a step of the mushroom breeding. So we have our germplasm, we have our strain with different genetic background. From this germplasm, from this strain, we harvest spores by spore print. We isolate single spores, and each spores will be identified, and we're going to select homokaryons or monokaryons. With these homokaryons, we make crosses that will give you an hybrid, and hybrid spawn will be produced, and each hybrid will be tested and assessed in our test units. So Sylvan is leading the market with the A15 strain. Nevertheless, we need to secure our market position by developing a new white strain. I have to say A15 is a hard one to beat, but we try to develop new white strain with an increased financial return by having a strain with a higher piece weight and strain that have a less spontaneous spinning that like 737 can be. We also want to expand our market, especially in brown, but we want also to create new opportunity for our customers. Until now, 18 patents have been filed by Sylvan on the development of new strain or the expansion of the germplasm. So I talked earlier about variation. What is variation? So the germplasm. So Sylvan holds the RRP collection. So we have almost 800 wild strain with different phenotype coming all over the world that can be used in our research program. I'll talk about accuracy. So we try to really to phenotype as precise as we can. It goes from vegetative stage, timing. Vegetative stage, the mycelium behavior in the compost, in the casing, the timing of the pinning, the yield, of course, but also the quality, the cap color, the shame, the stem shape, the bed attachment, or the bruisability. Bruisability on the cap for the white, and on the stem for the brown. All of this information help us to set up a KPI, and this KPI will be compared to the benchmark. For white, it could be A15 or 737. For brown, it could be Tuscan A20 or Heirloom. To help on this assessment, we have a new facility at Sylvan, the IDC, the International Demonstration Center, is in Horst in New Zealand. And this facility, it's a full equipped trial farm with 10 small rooms and two big ones. At IDC, we focus on the final stage of growing trial, and we encourage early stage collaboration with our customer, because we know when we launch a strain, for example, if we when we launched Tuscan A20, everybody wanted to cultivate it like heirloom, but it's a different strain with a different genetic. So we need to help our growers, our customers, to set up the cultivation, the blueprint and the cultivation parameters to avoid any waste of time of having the best performance. So at IDC, the crop care tried to work on the blueprint of the most promising strain. So we talk about time also. What we try is to speed up and improve the process. So for that, we have a lot of, we are fully equipped in molecular biology in our lab, and we use also the NGS, the new generation sequencing. So we use our genetic pool, we sequence, we align against the reference genome. From that, we can select SNP, so that can be potential markers in the future. We link this single nucleotide polymorphism, that means that's change in the DNA genome. We link that with a phenotype, and with that, we can have a better understanding of trait inheritance. We can have a definition of a better combination of parental groups, so we can choose easier and better the parents that we're going to choose for crossing. And we can define markers for a marker-assisted selection. What we do also is that we protect our innovation through patents or PBR. So the patent is a form of intellectual property. It gives us the right to exclude others from making, using, or selling the invention for 20 years. We use also PBR. It's mainly, could be in Europe, Australia, New Zealand, China, not in America. But that gives you, give right granted to the breeder of a new variety. It gives to the breeder the exclusive control over the propagating material and harvest material over a new variety for 25 years. So the IP is here to support the strategy of our business. Like every company, we have priority, of course, staying in the business, record ownership of all IP assigned to the company, and extract value from the company's IP. For that, we need to set up an IP strategy. And this IP strategy will help us to secure the freedom to operate, manage our IP portfolio. We can have the opportunity to license IP assets, but most of it we can make respect the IP right of our company. So we extract value from our IP. So there is several patents that have been filed for strains that have been launched. On white, we have the LB906, that strain for canning. It's it's mainly sold in Spain for now, quite successful in Spain. We have the S176, that's a new white strain that been commercially tested in China so far. And of course, we have the brown. So in brown, as you all know, the Tuscan A20 that's been commercialized mainly in Europe, Australia, and New Zealand. We have the Tuscan brown that's been sold in America. And there is a new one in the gang, it's Bavarian brown. So this is a new hybrid developed by Sylvan. So this new strain will give you high quality mushroom, higher piece weight, higher yield, and compared to A20, it can be less sensitive to compost quality. It's dark as Tuscan A20, but as you know, sometimes Tuscan A20 can get lighter, and this strain seems to be not tending to get lighter. So it's what we obtain from the traditional breeding that we have been doing for a few years now. But we think that we can use new technology as CRISPR-Cas9 for the mushroom breeding. A completely new era in breeding has begun because of this technique, the CRISPR-Cas9. Because it gives many things. It gives precision. You can target modification and reducing the off-target effect. You get efficiency. You accelerate the development of new mushroom strain. Most of the time in breeding, you need 2-3 generations to get a new strain. With this kind of system, you get directly the strain with the desired traits. And you have diverse applications. You can enhance the resistance to disease, improve flavor or texture, increase nutritional content or yield. So quickly, how does CRISPR work? So this system is derived from bacterial immune system. Is combined by two main components. So the clustered regulatory interspace short palindromic repeats, CRISPR, we're going to call it like that, and the Cas9 nuclease. So we have the single-gate RNA that consists of transactivating CRISPR RNA, which aids in Cas9 binding, and you have the CRISPR RNA that recognizes the targeted sequence. And then you have the Cas9 protein that will act as a scissor and nuclease. So when this complex binds to the target, the system allows the gene to be inactivated or replaced, who have its expression modified. CRISPR has been regulated in a different way over the world. So it will depend on the method of repairing the double-strand break. I won't go into detail, but when you break a DNA, a system is going to repair it, and there is a different way to repair it. In USA, CRISPR organisms are deregulated as much as far as any transgene, meaning foreign DNA, is being introduced in the organism. Otherwise, it's been considered as GMO. In Australia, only one type of CRISPR organism is deregulated, even if I think that from the first one and the second one, it's very difficult to discriminate, but it's deregulated only when it does not involve any transgene or repair template. And in New Zealand, it's like European Union, or all CRISPR organisms are regulated. CRISPR-Cas9 has many applications in agriculture. It holds significant promise for revolutionizing agriculture by having a precise genetic modification. So as I said earlier, it can enhance desirable traits. And there is some example of CRISPR organisms already that been created. You have corn with an increased yield, golden rice, rich in beta carotene. You have soybean with maturation promoted, or potatoes with elimination of amylose starch that can be useful for paper industry, for example. There is also a CRISPR mushroom that's been created. It was back in 2016. Agaricus became the first genome-edited organism to evade US regulation, USDA, on genetically modified organisms. How this CRISPR mushroom was made. So there is 6 PPO genes that's been involved in the bruising. And one of it was a knockout by CRISPR system, and that reduced the enzyme activity by 30%. Unfortunately, it seems that it also knocked out crop productivity, but it's hard to say more because actually this CRISPR mushroom has never been in the market, and there is no patent or genetic publication on it. So there is another CRISPR mushroom that be done in China in 2020. The Sweet George University in China report successful agaricus CRISPR editing. For this one, we have a patent and a paper. So the group utilized the agrobacterium vector for the transformation of the agaricus bisporus, and it targets the PPO4 genes. And the edition of the gene was verified by DNA sequencing. However, they reported in the publication that the PPO transformants were sick and slow growing. So PPO4 might have a role in the metabolic, way. The efficiency of transformation was low. A very few number of transformant was found. So we don't know if it constitutes a viable system. At Sylvan, we also started a few years ago to work on CRISPR. It's mainly done in America. So the part of the job was to understand the cutting-edge techniques and to see how it could fit in the future of our industry. We use CRISPR this past year by using agrobacterium system. For that, we collaborated with the University of Sydney. We have tested a number of designs, and the bottom line is that, like everyone else, we have found the process very tricky in the agaricus bisporus. So for the technology to become part of our breeding toolbox, we need a breakthrough, a reproducible method for CRISPR editing with high efficiency. Unfortunately, we are not there yet, but we keep working on it. The results are complex due to the multinucleate mycelium, and the analysis is time-consuming. The editing is random and very variable. So we really believe that CRISPR can be the future, and we can also use it even to dig more like in gene function to really understand which gene is responsible for what, and that will help also the traditional breeding. But work are still a lot of work still need to be done. So we use another technology to knock out gene. It's the RNA interference. This is a biological process which RNA molecules are involved in sequence-specific suppression of gene expression by using a double-strand RNA. So this small double-strand RNA is 21 to 25 base pair, and it targets a specific gene. So this small RNA will be recruited by a complex called RISC, and the duo scRNA RISC complex will bind the mRNA that will lead on the cleavage of the mRNA that will induce the reduction of the gene expression. So we got some data. So in Sylvan, we work on the PPO3 and PPO4. So I remind you, this gene are involved in the bruising. So what we try is to reduce the bruising by reducing the expression of these genes. So the Dr. Loftus in America and his team designed some construct to attenuate PPO3 and PPO4. We obtained 20 transformants with reduced bruising. And from among these 20 transformants, we have the best strain, 1F511, that's been tested 3 times for bruising and shelf life. And we saw a significant reduction on bruising and a longer shelf life. Nevertheless, we think that the effect on the shelf life is too small and is not still a real breakthrough. We still tested the attenuation of the gene expression to really see if this extension of shelf life was linked to a reduction of the gene expression. And even if the control might be reduced a little bit as well, it seems that it works. So we think that we need to screen a larger number of transformants to select a strain that will have a higher effect on the shelf life. So that is the work that we are doing on agaricus. I wanted also to show you a little bit what we are doing on exotic. So there is some slides about shiitake and proteus. So we started the breeding program on shiitake 4 years ago. We have like more than 50 shiitake strains in our collection, white strains coming from different places, like China, Korea, Europe. But it's very difficult to know the origin of the strain because most of the time could be copy of a copy. So we need to know if we have genetic diversity in our collection. So the whole collection has been sequenced using this new technology, the whole genome sequencing, Illumina opaque biosystem. We use 50 genetic markers to analyze the genetic diversity, and we were able to identify 8 genetic groups. So we have a target for now is to get strains that having better performance than our current commercial strains, the 4.325. So what we try to achieve is to have a shorter incubation, a better yield, a higher density cap, and we try to get different cap color. So we can have a light cap color for the Asian, even the Australian and New Zealand market, from what I heard yesterday, and a dark cap color for the European market. So far we tested more than 800 hybrids. We assess them in both pasteurized and sterile substrate because main of the market in Europe is pasteurized. For the rest of the world is sterile. We assess different parameters: the incubation performance, the timing, the yield, cap color, stem length, cap shape, the firmness, and the shelf life. So after less than 3 years, we were surprised, but we were able to develop a new strain, the SLX 328. The patent was filed in January 2024. This strain is suitable for the European market because it has a dark color and the quality is improved by an extended shelf life. But also for the Asian market where the production is on sterile because the first results show that we have a shorter incubation. I will finish with the proteus. So we work on developing a new sporeless proteus strain because we know that spores are continuously released in the atmosphere that cause respiratory allergies. And this allergy is caused by antigen present on the wall of the spores. And it's one of the most important limiting factors for large-scale cultivation of these species. So at Sylvan, we commercialized Popo. It was the first sporeless strain developed by Wageningen University, and it is exclusively licensed by Sylvan. Currently, it's leading the market. But we wanted to develop a new strain that's been owned by Sylvan. And so we started 5 years ago, I think, for this one. So we use a backcross strategy. That means that we use our LI strain. We use a sporeless mutant. We introduce the sporeless trait by crossing them, and after we do backcross to restore the phenotype of the LI strains. And we speed up the process by using molecular markers because we were able to design molecular markers that will help us to select progeny with the sporeless allele. And after 4 years, we developed SPX281. The patent was filed in 2023. It was pretty good in pre-commercialization. We did some trial with some customer in Greece, and it was launched on 2024. It's been currently cultivated right now, so in Greece, in Spain, in America, in USA, in Turkey. So this strain has great advantages. First of all, he doesn't produce spores. He has a very competitive yield to SPOPO, and his cycle is short. It doesn't really pin before, but he has a shorter interflash. That's shorter the complete cycle. And we have a reduced waste rate because we have a very short stem that's gonna reduce the waste rate. This is it for me. So I hope that that help you to understand a little bit better about what we are doing in Sylvan on the breeding program. And of course, if you have any question, I'll be very glad to answer.
Thank you very much.
Thank you. Thank you.
Thank you. And is there any questions from the audience? If there is, we might actually take some questions at the Sylvan stand, only just to catch up some time as we're heading into lunch, if that's okay with you. Dr. Amini, thank you. Thank you very much for your presentation.